Okay, in this screencast, we're going to really focus in on how the energy is moving um, in between the different trophic levels. And we're going to be looking actually also at the efficiency between those trophic levels and how to kind of look at that to see how efficient is the energy transfer from one trophic level to the next. All right, so back to this original slide. So we know that the energy is moving from the sun, converted in photosynthesis, to the plant material by primary producers as photosynthesis, right? And so they're fixing that light energy into chemical energy here. Now, that is going to then be eaten by the primary consumers and so on as you move up the chain. And you notice that generally in between trophic levels, we're going to lose about 90% of that energy to the environment because of the cell respiration happening. So the plants, they might fix 10,000 joules of energy, right, and make that available to these guys. But once they eat it, they're going to be using some of that energy, for cell respiration to make ATP, and a whole bunch of that is going to be lost as heat. So not every bit of the plants that they eat is going to directly turn into their biomass, right? Like if you eat a hamburger for lunch, all of that hamburger isn't going to be new biomass on you. You're going to eat that hamburger, and some of that hamburger or most of that hamburger is going to be used through cellular respiration. You're going to break it down and you're going to make ATP out of it, and heat is going to be lost. But the actual, even the matter part, right? The carbon in all of that, some of that carbon is going to be lost through egestion, which is actually going to pass through your system and you're going to get rid of it as a waste product. And then other parts will be as carbon dioxide. So what you're making, when you're making that ATP, a lot of that carbon gets changed into carbon dioxide, which you'll then breathe out. So that's why you don't weigh as much as the hamburger, 24 hours if you eat the hamburger. You don't gain that much more weight because some of it you're going to poop out and some of it you're going to breathe the carbon out as well. Okay. So again, during respiration, large amounts of energy are dissipated as heat. Okay. So in here, cell respiration, you're going to make ATP out of some of that, but you're going to get rid of a lot as heat. And that actually, all that energy allows us to maintain order. Like second law of thermodynamics, right? So we aren't dissipating into entropy because we're using all that chemical energy to maintain order within ourselves. Okay, now let's look at what that looks like in a caterpillar. So this caterpillar is a first level consumer and it is eating plant material, and it's going to say it's going to eat 200 joules worth of energy. Now, of that 200 joules of energy it's eating from the plant, only 33 joules are actually going to go into making new biomass for that caterpillar, right? 100 joules of that, the cellulose and all the parts that it can't actually digest, is going to be pooped out. This is called egestion. So a lot of that's going to go into the feces. This is now detritus. So that can maybe be broken down further by detritivores, but for now, just looking at moving from the producer level to the first level consumer level, we're going to lose a lot of that as actual detritus. All right, so 33 goes into new biomass, and 67 joules of that 200 is going to be ultimately lost as heat for cellular respiration. Okay, so when it's converting all that into ATP, and when that ATP gets used, the caterpillar is going to be exuding heat. So when you're doing cell respiration, like when you're working out and moving, a whole bunch of heat is getting released. That's why when you're working out, you're getting warmer. That's because you're carrying out a lot more cell respiration, which means a lot more heat is being released, okay? So all of that cell respiration is causing heat to be lost. So energy gets lost as heat. Only 33 joules then go into the growth of new biomass. Okay, so here's his low entropy because he's getting plenty of energy from organic molecules. He's going to use it to build complex molecules, create tissues, growth and repair. Again, more decreasing of entropy. And all of that's lost as heat. Heat's lower quality energy. Caterpillar or organisms can't use heat to drive cellular work. So it's actually kind of lost to the ecosystem. But something that I want you to think about is the efficiency of the energy transfer for this caterpillar. So what % of the energy consumed by the caterpillar is actually being used for growth? Can you figure that out? Hit pause, see if you can do it. All right, now you think you've tried it. So we've got 33 joules that they've used, right, out of a 200 total that they ate. and that's going to give us the efficiency. So we've got 33 divided by 200 gives us 16.5%. I multiplied it by 100 to get the percentage. So 16.5% of what it ate is the actual efficiency of turning it into biomass. You should be comfortable with being able to do that equation, being able to figure out the percent of something. So, what percent of 200 is 33? So you take the 33 and you divide it by the total of 200 and then multiply by 100. So it's 16.5%. Now we know when we were looking at those pyramids before, let me go back to our little pyramid here. When we were talking 90% is usually lost to the environment is heat. So the caterpillar at 16.5% is actually more efficient than our average because normally only 10% gets passed up. But if that caterpillar is having the efficiency of 16, then he's more efficient than the average, ecosystem. And that actually makes sense because caterpillars are what we call exothermic. They don't need to maintain their body heat. They're not wasting a lot of energy trying to stay warm like mammals and birds are. And so they can be pretty efficient with the calories that they eat, and they can turn a lot of those into biomass. Whereas mammals have to burn a lot of the food that they eat to make enough warmth to be able to stay warm. So we're not as efficient. But the exotherms are actually pretty efficient with their transfer of energy, unlike us endotherms who need to keep a constant body temperature. You're also going to see that the energy transformations in the water are pretty efficient as well because there's some nice insulation in the water there, and most of those organisms also aren't trying to maintain their heat. So for some ecosystems, the maintaining 10%, that's about an average. Some trophic levels might be more efficient or less efficient, just depending on what the organisms are that make it up. All right, but you can see if you were to do the calculations here, what percent do the primary consumers, how efficient is that? So compared to the trophic level before, so you've got 1,000 joules divided by 10,000 joules, and again, that will give us the 10%. All right. I'm going to have you guys work on this worksheet that's really kind of tracking energy flow through an ecosystem. So I just want to explain this worksheet a little bit if you want to pull it out and take a look. Here's all of the energy that is falling on the plant from the sun. So it's 7,000, and it's in kilojoules per meter squared per year if you're curious about the units. And how much gets absorbed by the plants is 1,700,000. But how much is actually fixed? So this is what's absorbed, but this would be how much is fixed into biomass, is 87,000. So in this trophic level of producers is 87,400. And then it's going to have you kind of work your way through and talk about what are these different, what's going on in each of these levels. Like how much of this is going to go into the primary consumers, right? But you can track how much is lost in other directions. So for the producers, they have 87,400 kilojoules per meter squared per year in that trophic level, and 50,450 is lost as heat, and 22,950 is lost as detritus. So how much then is left for the primary consumers to eat? Okay, and then for those primary consumers, what is left there for them, that much goes to heat, that much goes to detritus. So you just kind of follow your way through. There's some questions to answer. So you're just kind of looking for each trophic level. You can see how much is lost as heat and how much goes to detritus. And you got to think about kind of what are those energy efficiency transfers. All right, good luck.